In this lesson, we're going to use derivatives to describe how functions or curves are changing. I have a curve f of x here, and I've drawn a secant line to the curve as well as a tangent line to the curve. A secant line intersects a curve in exactly 2 points. A tangent line touches a curve at only 1 point. Now, if I want to describe how a curve is changing, let's think about how we describe how a line is changing. The rate of change of a line is the slope. And that's the formula for the slope of a line. So if I wanted to approximate how this curve is changing, I could find the slope of my secant line here, and my first x value, x1, would just be this first x where I drew the intersection of the line to the curve, and my second x value is over here, a distance h away from my original x. Then my y1 would be the function evaluated at x, and my y2 would be the function evaluated at x plus h. So the slope of the secant line would be f of x plus h minus f of x over x plus h minus x, which is f of x plus h minus f of x over h. Now, if I wanted to figure out the slope of the tangent line to the curve, I don't have 2 points to plug into the formula. Let's look and see what happens if I draw another secant line where my h is a smaller distance away from my original x. The slope of this secant line is a lot closer to the slope of my tangent line than my original secant line was. So what I see here, as h is getting smaller, my secant line is getting closer to my tangent line. Well, we can use a limit to describe this behavior, and the slope of my tangent line would be the limit as h, the distance between my x values, goes to 0 of f of x plus h minus f of x all over h. That is actually the definition of a derivative. A derivative describes how the curve is changing, and it is the slope of the tangent line to the curve if we evaluate it at a specific point. The notation for a derivative is f prime of x. We can also write that as y prime. And then if we are telling someone to take a derivative of a function, the command for that is to say d dx, take the derivative with respect to the variable x of the function f of x, and this results in another notation that can be written as dy dx. The derivative of y with respect to x is what that said. So all of these are the results of derivatives, and this one is a command telling you to take the derivative. Okay, so let's use this formula here to find the derivatives and slopes of tangents to some curves. All right, so we want to find the slope of the tangent line to the curve 2x minus 3 at the point 2, 1. Now, let's think about this. F of x equals 2x minus 3. That's a line, and it's a line with a slope of 2. So when all's said and done, we better get 2 as the answer for the slope to the tangent line to a line. They should be the same line. We're going to use our formula, though, for a derivative. which is the limit as h goes to 0, of f of x plus h minus f of x all over h. Well, if I'm going to do this, the first thing I need to do is figure out what f of x plus h is. So we're going to substitute an x plus h into our original function. I'll distribute the 2 and I get 2x plus 2h minus 3. Now I can plug this in here. And find the derivative. So I plug in my f of x plus h minus f of x. I'm going to subtract the original function, which is 2x minus 3, all over h. And if I distribute this minus here, I get 2x minus 2x, negative 3. This will turn into a plus 3 here, and I'm left with the limit as h goes to 0 of 2h over h, which simplifies, to the limit as h goes to 0 of 2, which is 2, which is what we said we should get, knowing that it was a line with a slope of 2 to begin with. Okay, let's try one that isn't a line. F of x equals x squared plus 1. So this is actually a parabola that opens up. And we're just asked to find the derivative. We're not finding the slope of a specific tangent line because we aren't given a point on the curve to find the tangent line. So we're going to find the derivative, which tells me about how the curve is changing everywhere. So, first thing I need to find is my f of x plus h. So we're going to evaluate the function at x plus h. I plug that in for my x, and we're going to have to multiply this out. So I have to multiply out x plus h times x plus h. That gives me x squared plus xh plus another xh plus h squared. So this is actually x squared plus 2xh plus h squared, and then we have our plus 1. So if I plug into the formula for a derivative, we plug in our f of x plus h, which is x squared plus 2xh plus h squared plus 1, minus our original function, all over h. So we're going to distribute that minus. And I keep my limit notation until we do our direct substitution. And so I'm going to distribute that minus. We get minus x squared minus 1 all over h. And then I see that x squared minus x squared goes to 0, plus 1 minus 1 goes to 0. And what I'm left with is 2xh plus h squared all over h. Now, if we've done this correctly when we're finding a derivative, we should always be able to factor out an h and cancel it with the h in the denominator. Otherwise, we'd be dividing by 0 when we do the direct substitution. So, if I factor out an h from my numerator, I'm left with 2x plus h all over h. This h over h goes to 1. And I've got the limit as h goes to 0 of 2x plus h. When we substitute in a 0 for that h, we get 2x. And that is the derivative of my curve, or how it is changing anywhere on that curve.